Welcome back, everybody. So today I'm going to be talking about qubitization, one of my favorite topics. And in particular, what we're going to be doing is we're going to be showing how we can derive the walk operator based on qubitization. And then I'm going to spend a couple of words talking about how the quantum singular value transformation can be used in order to be able to convert this from an algorithm that can be used in order to estimate eigenvalues into something that we can actually use to do dynamical simulation. So let me begin by sharing my screen. Wonderful. Okay, so the key thing behind qubitization is qubitization uses exactly the same kind of interface or oracles that LCU ends up using. So in particular, there are two operations. Prepare, which I'll shorten to be prep, that will take a qubit register containing 0 and end up yielding sum over j square root of alpha sub j over square root alpha j, where we are going to define our a operator, let's call it h, is equal to sum over j equals 1 to, say, I don't know, m, alpha sub j, u sub j. Further, we're going to assume that we have a select operation. And what select will do is select will take a state j psi for any arbitrary psi, and it will map that to j u sub j psi. Okay, then with these two operations, what we're going to do is we're going to actually define a walk operator. And this walk operator is going to look a little bit like the walk operator for amplitude amplification. It is of the form identity minus twice prep 0 0 prep dagger tensor identity times select. So if select were a reflection, then this whole operation will end up actually taking the form of a amplitude amplification like circuit. So W is a product of two reflections, which we saw from our previous analysis implies that it would induce a rotation on a 2D subspace. Okay, so that's what we expect. However, in full generality, select applies an arbitrary unitary, and those unitaries need not necessarily be reflections, but actually turn out to be reflections in most of the cases that we care about, such as chemistry simulation and other areas. However, in this particular case, we're not going to necessarily end up making that assumption. But I wanted to mention this just to build some intuition. So the basic idea that of qubitization is it turns out that this W operator, it has eigenvalues of the form e to the plus minus I arc cosine of lambda j divided by alpha, where h acting on it's eigenstates, it's called jth eigenstate lambda j is equal to lambda j lambda j. Okay, so these are eigenvectors of the Hermitian matrix H. And because H is a Hermitian matrix, all these eigenvalues exist, and lambda j is real. So this ends up giving us the eigenvalues for this. And the key thing that this ends up doing is this implies that phase estimation can be used to learn lambda j from this. And so that's the whole idea behind at least the most naive way that people will end up using qubitization in practice. So if you don't pay attention to the rest of this lecture, this is kind of like the most important thing to know about qubitization. But of course, there's a lot of extra details that we're going to be going over in order to understand why exactly this is the case. Now, the analysis for it looks pretty much actually identical to the analysis that we used behind amplitude amplification. So to begin, what we're going to need to do is we're going to need to intuit what these two-dimensional subspaces that are going to be created by the walk operator are going to look like. So let's just kind of intuit it and guess that the eigenstates are of the form, or at least the relevant eigenstates are going to be of the form phi, and I've already used a little bit of jargon here, so just bear with me for a second, lambda j, where phi is just defined to be equal to prep acting on zero. I'm going to be referring to prep acting on zero a ton in this. And so just in order to be able to save time for you all, I'm going to define phi to be the action of prep on zero. Okay. Now, this isn't exactly quite true, but the idea is that we're going to guess that kind of like the initial eigenstates are going to be actually supported by this and another vector. The other vector that we're going to I should say, in the support of this. The way we're going to find the other vector is inside that we are theorizing will span the two-dimensional subspace that this phi lambda j is in, will be in the following way. We're just going to use Gram-Schmidt orthogonalization. So we're going to take a look at W dagger acting on phi lambda j minus the projection of this onto the original state. And the projector is onto the original state is obviously of the form lambda j W phi lambda j divided through by a normalization constant that I'll call eta. And the eta is just whatever number we need in order to make sure that this is, in fact, a valid unit vector. And we're going to define this unit vector to be, let's call it phi sub j perp. Okay. So this is our operator, but we can actually end up simplifying this to be identity minus the projection onto phi tensor, the projection onto lambda j times the adjoint of W acting on lambda j. And you might ask why we use the adjoint here, because basically what it turns out that it's just mathematically more convenient to argue about the inner product between this and the original operation. So this is our action, or sorry, our other space, our state that we want. And if W constrained to phi lambda sub j and phi sub j perp is a unitary matrix, then the assumption that we are in, or sorry, that its dynamics resides in a 2D subspace for each phi lambda j is valid. Okay, so specifically, how are we going to go about analyzing this? Well, the way that we analyze this is just by taking a look at the matrix W evaluated inside this two-dimensional subspace, which I'll denote by this block matrix language. And the matrix W inside this subblock can be written as phi lambda j w phi lambda j. So I'm just computing actually all the individual matrix elements that we end up getting in it. And then this is phi lambda j w phi j perp. Then we have phi j perp w phi lambda j. And then we have phi j perp w phi j perp. Okay, and so now we're going to go through and work out the matrix elements. It turns out that for practical reasons, or just in the interest of saving time, I'm only going to discuss evaluating these two matrix elements. The remaining two are pretty much exactly the same. So the way that we're going to evaluate these is as follows. First thing, let's work out what phi lambda j w phi lambda j is equal to. Well, this, using the definition of W, is equal to phi lambda j identity, the minus sign out in front, minus 2 phi phi tensor identity times the select operator. So all I'm doing here is, if you recall, I'm jumping back to the definition that we ended up making for W right here, and simply substituting that in. Okay, then we compute the matrix element of this in lambda j. Okay, well, there's a couple of things that are really kind of straightforward with this. First, this is a reflection operator, and further, it's Hermitian. And so that means that its action on a vector to the right is exactly the same as its action for a vector on the left. In particular, what I mean is, if A acting on X is equal to negative X, then X, just by taking the conjugate transpose of this exact same operation, will give us negative X. So using that property, we end up seeing that this whole thing actually can be rewritten as phi lambda j without the projector, and just select acting in the middle. Now, phi over here, actually, all of this can be rewritten in the following way. We can rewrite this as phi tensor identity times select and phi tensor identity on this side, and lambda j, just by effectively factoring the lambda j out. However, recall that phi is equal to prep 0. Under that, this circuit up here actually can be thought of as just a linear combination of unitary circuit, where this whole thing is just simply the exact same form as the following. This is saying, okay, let's prepare 0 up here. We'll prepare lambda sub j down here, and then apply prep, select, then prep dagger. And then we'll project this onto 0. So that is the particular outcome that whose amplitude this is measuring. However, this is a linear combination of unitary circuit. And we showed in a previous lecture that this actually ends up giving us simply lambda j h divided by alpha lambda j, which of course is equal to just lambda j over alpha, because we assumed that h acting on lambda j is just lambda j, lambda j. Cool. All right. So that is the first matrix element for this. So this matrix element is equal to lambda j. Now we can actually take it one step further. So B, for the first, for matrix element B, what we need to be able to do is we need to be able to, of course, compute the inner product between phi, lambda j, w, and phi j perp. Now, phi j perp, we didn't fully define phi j perp. And the reason why is we didn't define what the normalization factor is. And that normalization factor is actually going to be kind of important here. So let's work that out. So we require that phi j perp is equal to 1. And this actually has to be equal to, just from the definition going back up of phi j perp, it's got to be the inner product of this with respect to itself. So this is equal to phi lambda j times identity minus the projector onto the space, which was phi tensor lambda j. And now we need to multiply this by the walk operator. We've got to take the adjoint of the adjoint here, so that will just actually give us W. Acting on the state. Let me just make sure that I'm getting this right. Oh, sorry, actually, I need to have a W adjoint here, or no, actually, this is just W. Now, the next term that we get is just the definition of phi j perp. So all of this is going to be multiplied by the projector onto the state, phi times W adjoint acting on phi lambda j. Okay, but because of the fact that this is a projector, and any projector squared is equal to itself, we can note that these two projectors kind of end up, let me actually just fix this. This is lambda times identity minus phi tensor lambda j w perp. So therefore, this is equal to phi lambda j w identity minus, oh, and this is all divided by eta, the normalization constant eta squared. Identity minus phi tensor lambda j w adjoint phi lambda j, divided all through by eta squared. So now let's distribute this through. What we're going to do is we're going to take a look at the identity term and the w adjoint term. The identity term is just going to give us, well, let's just factor out the 1 over eta squared to begin with. We'll get phi lambda j w adjoint phi lambda j minus phi lambda j w phi lambda j phi lambda j w adjoint phi lambda j. Okay. And so this, of course, first term is equal to 1. This term is equal to lambda j, as we reasoned previously. This term also has to be equal to lambda j. And why is that? Well, the reason why is that this term is equal to the complex conjugate of the previous one. And so because this is equal to the complex conjugate and lambda j is real because it's an eigenvalue of a Hermitian matrix, which is always real, this ends up giving us 1 minus lambda j squared. This implies that eta has to be equal to 1 minus lambda j squared. And therefore, all right, so eta squared has to equal that. And this implies that eta is equal to 1 minus lambda j squared square root. Okay, good. So now what we need to do is we need to actually go through and reason about what the inner product is to find the upper right matrix element of this. So we need to figure out this guy up here. So our result is that phi lambda j w phi j perp is equal to, of course, phi lambda j w identity minus the projector onto the initial state, or at the very least the eigenstate, acting on the w adjoint, acting on phi lambda j. And now we've got to divide this through by eta, which we've now identified as 1 minus lambda j squared, all square rooted. Wonderful. So just like before, we go through and we figure out that this actually, from the exact same reasoning, it ends up giving us square root 1 minus lambda j squared. And from this, we see that w is in fact actually equal to lambda, oh, I'm sorry. Actually, I forgot about the normalization constants, alpha in here. Yeah, good. I got it there, but I just didn't copy the alphas down in the rest of it. So this is lambda j over alpha, square root of 1 minus lambda j squared divided by alpha squared. And the rest of these elements turn out to be minus 1 minus lambda j squared over alpha squared. And this one turns out to be lambda j over alpha, just like the previous one. Okay, so this matrix actually might look really kind of familiar. So one thing that we can do is let's define theta to be equal to the arc cosine of lambda j over alpha. Then, using this notation, the walk operator w can be rewritten as cosine theta sine theta minus sine theta cosine theta. All right, so this is, you can see, this is actually equivalent to ry of -2 theta. The eigenvalues of the ry operation are actually just e to the plus minus I theta, which is in our case equal to e to the plus minus I arc cosine of lambda j over alpha. Okay, so what this ends up meaning is that this verifies our claim about the eigenvalues of the W operation constrained inside this particular subspace. And further, because W is unitary, we end up seeing that the hypothesis that we assumed that W acting on phi, or W to the K acting on phi lambda J remains in the 2D subspace spanned by phi lambda J and lambda J phi J perp for all K. So this ends up justifying the fact that for every such vector, we actually don't need to fully diagonalize the matrix. We only need to be able to identify these two vectors that are in its support. And so that ends up leading us to the following formal statement of the previous observation. Let H be a Hermitian 2 to the n by 2 to the n matrix. And let W equal minus identity minus 2 times state phi tensor identity select. Then for all lambda j such that H acting on lambda j equals lambda j, there exist two vectors. Let's call this chi j plus and chi j minus, such that phi lambda j is equal, yeah, sorry, these two vectors obey this such that W acting on chi j plus is equal to e to the I arc cosine of lambda j divided by alpha, and W acting on chi j minus is equal to e to the minus I arc cosine of lambda j over alpha. And further, and we have that the vector phi lambda sub j is equal to beta chi j plus square root of 1 minus beta squared chi j minus 4 some value of beta less than or equal to 1. All right, cool. So that is the formal statement of what qubitization ends up doing. And the question is, well, how can we apply it? So there's a couple of things that I want to mention about this first. First thing is, we require that H is Hermitian. We can actually apply the same sort of reasoning in order to be able to use this to be able to also address the case of non-Hermitian operators under some circumstances. So let's say we have a matrix A. Then we can, for any matrix A, we can define H prime is equal to 0, A dagger, 0. Then from this definition, it's actually pretty straightforward to see that H prime squared, then is equal to A dagger 0, 0, A dagger A. Okay. And you can see that this ends up forming two irreducible blocks over here. Thus, the eigenvectors, well, first, the eigenvectors exist for this because of the fact that this is a normal matrix, and the eigenvalues associated with those are just going to be the eigenvalues of the of A dagger A or A dagger. But the eigenvectors in particular can be written as in the form, let's say phi j 0 yeah, or 0. Okay, let me just actually make sure that I'm doing this right. Yeah, so let's actually write this in block form. So if we're writing this in block form, the eigenvalues can be expressed, the eigenvectors can be expressed as this, or psi j, where psi j is an EV of A dagger A, and phi j is an eigenvector of A dagger. So what this ends up meaning is that the singular values of of H prime are the same as A. So if we do this in the context of a non-Hermitian matrix, we can actually do exactly everything that we've laid out here. But instead of getting the eigenvalues of H in the above operation for lambda j, now these will still be the eigenvalues of H, but those will now correspond to the singular values of the matrix A. So we can use this to figure out singular values of an arbitrary non-Hermitian matrix. Okay, that's already pretty cool. But how do we figure out eigenvalues? So the way that we can do this is the following. We have an operator, W, and W will end up mapping phi lambda j, which is equal to phi beta chi j plus square root of 1 minus, actually, I'll put a j in here for reasons that will be clear later, chi j minus, and this, of course, will end up getting mapped to phi beta j e to the I theta j, or let's actually just write this all in. This will actually be the arc cosine of lambda j divided by alpha, acting on chi j plus square root of 1 minus beta j squared, e to the negative I arc cosine of lambda j divided by alpha chi j minus. All right, so we can see that this is, again, a superposition of two different eigenvectors of the walk operator. In fact, actually, more generally, let psi equal the sum over j of, let's call it aj lambda j. Then this initial state, phi psi, we can actually just rewrite as the sum over j, aj times phi. Actually, I'm going to rewrite this. Yeah, okay. Let me rewrite this as beta j phi chi j plus square root of 1 minus beta j squared chi j minus. All right, so this is our resulting state. And so what we can do is, if we apply phase estimation to this, we saw that PE will map each of these vectors to something that will be of the form sum over j, a sub j, beta j, 1 minus okay. What I'm going to do, just for the case of just for simplicity for our discussion at the moment, I'm going to neglect error. So let's neglect error in the phase estimation process, just to be able to describe what happens. So this would happen only if the eigenvalues are precisely roots of unity, as we ended up seeing earlier. If they're not quite, then the quantum Fourier transform will lead to some small error that we can, of course, make arbitrarily small, but for the sake of simplicity, let's just ignore it. So when we apply this idealization of phase estimation to this, what we'll end up getting is we'll end up getting beta sub j, phi, chi j, and the encoding of the eigenphases for the operators. These eigenphases are, of course, plus minus the arc cosine of lambda j over alpha. And so I'll represent that information in this binary encoding of the arc cosine of lambda j over alpha, plus, of course, the square root of 1 minus beta sub j squared of phi, and this will be plus over here, chi j minus, and then the state, that phase estimation will encode over here, neglecting errors, of course, will be a binary encoding of negative the arc cosine of lambda j over alpha. So if we end up measuring, then we'll project ourselves down into one of these particular values. So by measuring, we will get, with probability, a sub j squared, beta j squared, we will get, after measuring, again, neglecting errors in the phase estimation, we will end up getting the state phi chi j plus cosine or arc cosine of lambda j over alpha. And then what we can do is we can actually just work backwards. We've got now this binary string in here, and we can figure out what the actual value is going to be of lambda j. And the way that we do it is I'm going to make an estimator, lambda j estimator, and we'll take this value over here as being our estimate phi hat. And so this lambda j estimator is going to be just alpha, which is a known constant for all such problems, alpha times the cosine of phi hat, theta hat. Okay, but phase estimation returns with probability greater than or equal to 1 minus delta, a value that is going to be theta hat minus the arc cosine of lambda j over alpha, absolute value, less than or equal to epsilon, if at least if at least order log 1 over delta over epsilon applications of W are used. And let's just call this epsilon naught, or epsilon sub theta over here. The reason why I'm calling it epsilon sub theta is that we want to figure out how the scaling of epsilon theta is going to have to scale in order to guarantee that our error in the final estimate is at most alpha. So this ends up meaning that our estimate with probability greater than or equal to 1 minus delta, our estimate will satisfy that lambda j hat minus lambda j will be absolute value will be less than or equal to alpha cosine of theta, which is just the arc cosine of lambda j over alpha, plus epsilon theta minus the actual eigenvalue lambda j. Okay, but cosine is Lipschitz continuous with Lipschitz constant 1. And you can see this because the cosine function is, of course, differentiable with its maximum derivative equal to 1. Therefore, it's Lipschitz with constant 1. And so from this, we can end up seeing that this expression over here is upper bounded by alpha epsilon naught. Okay, so that is the basic expression that we need. And so if we want this to be less than or equal to epsilon, then it suffices to pick epsilon naught equal epsilon over alpha. And this implies that the total cost of phase estimation is in order log 1 over delta over epsilon times alpha. Okay. Now this actually leads to the best known methods for simulating, for example, chemistry on quantum computers. Okay, so this technique has actually been responsible for reducing, along with several other insights, the costs of quantum simulation down by, for finding the minimum ground state energy of molecules down by about 5 orders of magnitude from the previous methods that had been proposed. So the importance of this technique for simulating physical systems, where in many cases, all you want to do is figure out what an eigenvalue is for that particular system, that's phenomenal. The other thing that I should mention is that the eigenvalue that you end up getting out of it is largely dictated by the support of the initial state onto the particular eigenvector in question. So that's where this AJ squared is. So the the probability of you getting, say, the lowest energy eigenstate really depends on what the overlap is, this value of AJ squared with the ideal state that you want to find. So if you build a state that's really close to your target, then AJ will be about 1. And with extremely high probability, then you'll either get the chi plus state or the chi minus state. Either way, because cosine is an even function, when we apply it to this particular function, then we'll actually end up getting the exact same estimate coming back out because of the parity of the cosine function. So these are some really good features. But the next thing that I like to talk about is simulating e to the negative IHT. So how can we do this? Well, the big hint behind how we can do this is actually just taking a look at what the eigenvalues of chi plus and chi minus. They have eigenvalues e to the plus minus I arc cosine of lambda j over alpha. And so if we could take this value, and this value we'll call theta, which is equal to the arc cosine of lambda j over alpha, and map it to cosine theta, then W acting on chi plus would, or let's call it chi plus tilde for the transformed version, would end up giving us or I should say, our transformed version of W. If we could transform W in such a way as to do this, then we would end up having that this would be e to the cosine of arc cosine lambda j over alpha of an I here, chi plus, which is just actually equal to e to the I lambda j over alpha, chi plus. Cool. Well, if we also were able to do this to chi minus, then we end up seeing that this is e to the negative I, or e to the plus I, minus, or cosine of minus arc cosine of lambda j over alpha, chi plus. But again, because this is even, this actually is just e to the I lambda j over alpha, chi plus. So then something kind of magic ends up happening. If we could build this operator that's exactly the same, except its eigenvalues have been transformed to kind of like cosine of those eigenvalues, at least in the exponent, then what we would end up doing is we would have that W tilde acting on the state phi lambda sub j would be equal to W tilde acting on the state phi times beta sub j chi j plus square root 1 minus beta j squared chi j minus, which is actually just equal to e to the I lambda j over alpha chi plus, beta j chi j plus square root 1 minus beta j squared chi j minus, because we just argued that both of these vectors have exactly the same eigenvalue now that they've been transformed. And this actually is the exact same thing as e to the I lambda j divided by alpha acting on phi lambda j. So therefore, we have W tilde has phi lambda j as a eigenvector. Further, the eigenvector has eigenvalue proportional to the state. So W tilde acting on phi lambda j is actually the exact same thing as phi times e to the I h over alpha acting on lambda j. So we can see that actually what we're doing is, apart from this tensor factor, which is kind of just kicking around for the ride at this point, it's not doing anything other than allowing us to use this W tilde operation. This is actually the exact same thing as the dynamics for the e to the IHT, where t is equal to 1 over alpha. So the way that we can end up doing this is by using a beautiful formula. And this formula is called the Jacobi Unger expansion. Now, if I were smart, I would have written this down in an intelligent way. So, oh, yes, those are the geeky web comics that I warned you all about. So, Jacobi Unger expansion. So, the Jacobi Unger expansion is, let's just copy this out. How? Okay. The Jacobi Unger expansion is this guy over here. And so this says something pretty amazing. Let's take Z, because Z in this formula is an arbitrary constant. This says that we can write e to the I cosine of theta as the sum from n equals negative infinity to infinity of I to the n jn of 1 e to the I n theta. And further, we have that jn of 1 ends up scaling kind of like 1 over n factorial. So this is a very rapidly decreasing function. And these jn's, I should say, these are Bessel functions. So these are just numbers that you can end up looking at. And worst case scenario, they scale kind of like 1 over n factorial. So this is a really rapidly converging series. But further, we can actually use this exact same expression to end up saying that if we have that, that our operation W tilde that we ideally would like to build, we can use this exact same expression because W tilde is the cosine of the eigenphases, or has the cosine of the eigenphases of the original operator. We can build this as a linear combination of unitaries using this expression, W to the n. All right. So this ends up giving us our eigenvalues. And as mentioned, the values of theta for this, theta sub j, are equal to, of course, our cosine of lambda j over alpha. And so when we take the cosine of these, we end up seeing that these get mapped to the corresponding eigenvalues for W tilde, which will be equal to the cosine of the arc cosine of lambda j over alpha, which will give us the correct result. So we can see that the cost of doing this using linear combination of unitaries implies that the cost basically ends up scaling like order log 1 over epsilon queries that we end up needing in order to be able to make this whole thing work. And the result is e to the I h over alpha. Repeating this t over alpha times gives a cost of order t, alpha times t times, because it's divided by this, we get a cost that goes like alpha t log 1 over epsilon, which ends up actually tying the cost of doing a simulation using the truncated Taylor series method. But this requires actually a much simpler control than we would require for the truncated Taylor series approach. It can further actually be optimized, and to the optimal form of this actually can be done using the kind of more advanced quantum singular value transformation techniques. These use order 1 ancillary qubits and need time order alpha t plus log 1 over epsilon. So they turn essentially, the biggest difference is they turn this multiplicative logarithm into an additive logarithm, which is really kind of awesome. So, these techniques, were originally pioneered by Schwang and Low. And in particular, you can see a nice kind of summary of all of these advanced methods in the Gillian Su Low Weeb paper on the quantum singular value transformation. So basically, there's a slightly more optimal way of doing it, but I expressed it like this because of the fact that this is a far easier way to understand how you could transform it back than using a slightly more optimal approach in these other papers that's a little bit more complicated. So that is qubitization in a nutshell. And it is a fantastic way for you to be able to come up with an easy way of learning eigenvalues of particular matrices that further, with the use of the quantum singular value transformation, you can use in order to be able to transform into actually a form that we can use in order to get optimal or nearly optimal quantum singular value quantum simulation methods. So thanks a lot, and yeah, see you all next time.